Log on, tune in, find out. Another good idea from Cambridge.
This is Christian Mercat from Montpellier, who will talk on linear and quadratic discrete holomorphic functions as integrable systems.
Thank you very much. Good afternoon. Thank you for the organizers for inviting me to this very nice program. So I'm going to talk about discrete Riemann surfaces as integrable systems. Oops, sorry about that. So it's mainly joint work with Sasha Bobenko and Yuri Suris. So the connection with this discrete integrable system program is mainly it's quite simple actually. It's about a complex version of a discrete Mutter equation, and the so-called Q1 delta equals 0 first ladder in this Adler-Bobenko-Suris hierarchy of discrete integrable systems, which was, this particular equation was already known for quite a long time. In the light of the study of these two simple integrable systems, in the light of discrete complex analysis, okay? So, and some very special functions, which were called discrete exponentials, are going to play a prominent role in this talk. So first of all, if you want to discretize Riemann surfaces and holomorphic functions, you've got to understand what holomorphic functions are. So of course you all know what they are, but I want just to show you some pictures in order to have a pictorial understanding of what it's about and how we can discretize that. So holomorphic function is a function from the complex plane to the complex plane. So here I've paved the complex plane with a picture of Newton with this heraldic sign of Cambridge, the Université of Cambridge, and then I transform them by this holomorphic function. So here is the identity. Okay, the identity is holomorphic function, and so now the next step are similitude, where you have translations, rotation, and homotopy. So a holomorphic function is locally a similitude, and the zoom factor is called the derivative of the function. So there are some. So such functions are called conformal because they preserve angles. So any holomorphic function is conformal except at zeros, okay, where the function has a zero, and here the zoom ratio is null, so it's not conformal at that point. So, and what you see as well here is that this function is obviously not injective; it's 2 to 1. So you have every point here is sent to the same point as its opposite. So you have 2 points sitting on the at the same point, and they are sent to the same point. Okay. So if you want to discretize such a thing, if you want to have here a polygon here be sent to an image of a polygon, and you want to say that this polygon has a zero for the two around the. If you have, let's say, a triangle here, it will not be sent to a triangle circling around 0. That's not possible. So there will be problems of getting to know the order of a 0. So if you want to be injective, you can just take half of the picture, let's say the positive real part, or you can take as well the negative part of the picture. But okay, so but then you've got these blood pictures for the whole plane. So one way to have a nice picture is to actually take the pull back. That is to say, you take a point z here, you apply the function f of z, you get there, and you take the value of a pixel z to be the value of the pixel f of z. And then you've got nice pictures, and it's easier to understand. So, of course, you've got zeros of higher order. So here, to discretize such a thing, you'll have to have polygons of even more sides. If you want to say that inside this polygon there is a 0 of order 3, you'll have to have at least 9 sides. Okay, so you then next functions which are interesting in complex analysis is the inversion. So here you see that at 0 it goes to infinity. Well, how do you discretize that? Of course, you're not going to require that at some point the value is blowing up to infinity. So you've got to come up with other ways of having simple order poles. And you can have poles of higher order, and things get more complicated even in the discrete case. And I don't know how to deal with the higher order poles. But you need such things, such poles, in order to define things like tangent or whatever, rational fractions, which have poles at different places. Another very important function is the logarithm. So it's as well going to infinity at 0. So we'll see how this can be done in the discrete case. This is actually called the green function, and it has a discrete counterpart. So this is the view of logarithmic singularity in general. Then you've got its pullback. It's reciprocal, which is called the exponential, and we'll see that the exponential are going to play a very important role. Many more complicated things can happen to meromorphic functions. You can have a essential singularity here with an accumulation of zeros and poles, and of course I don't know how to do that in the discrete case. Okay, so there's going to be plenty of graphs, and I claim that quadrilateral graphs are really good. And why are they so? Because actually they capture in 2 dimensions at least, because they capture most of the combinatorics. Let's say you have a graph, okay? So a graph on a surface, okay? It's a 2-dimensional graph. It's a planar graph, locally planar graph. So you have vertices, edges, and you can, because it's on the surface, you can build its Poincaré dual. This is a combinatorial thing, okay? So you put a dual vertex inside each face, okay? For each edge separating 2 faces, that is to say 2 dual vertices, you have a dual edge. That's the dual graph gamma star, okay? And the dual graph gamma star. So when you take both at the same time, and that's what I'm going to do, then you have another type of thing, the double graph, okay? So the double graph is where I'm going to put my things. So when I'm talking about discrete holomorphic function, it's taking place on the vertices and on the dual vertices at the same time. That's a bit tricky when you begin with it, but you need it. Another way to look at it is actually to relate vertices and dual vertices, that is to say the center of the faces, and then you have a graph made out of quadrilaterals. Okay? So that's why I'm saying that the main interesting things we are going to deal with are quadrilateral graphs, okay, quad graphs. Okay, so on this quad graph, we're going to put a discrete version of the Cauchy-Riemann equations. Okay, so so a function f is conformal. We've seen if at the first order it's a similitude. Okay, how do you recognize the fact that you have four values in the complex plane, and they are sent to 4 other values in the complex plane? How do you recognize that they are linked by a similitude? Well, one way to do it is that the ratio of the diagonals, okay, the difference divided by that difference, is the same as the one you begin with. Okay, so you have a a graph in the complex plane with complex numbers sitting at the vertices, you send that to another place in the complex plane, and you want to say that it's mapped by a complex, discrete holomorphic function whenever the image of the diagonal ratio is the same as the diagonal ratio you begin with. Okay? Actually, there is a quadratic version of that. If you look at what are conformal functions in the quadratic term of it, then you'll see that a function is conformal when it's locally a Möbius transformation. Okay, and how do you recognize Möbius transformation? When one way is to look at the cross ratio. Whenever the cross ratio of the image is the same as the cross ratio you begin with, then you're going to say that it's a discrete conformal in the quadratic version. And this equation here is actually the Q1 delta equals 0 ABS equation. So it appeared in the 80s in a paper by Capelli and Neyhoff, if I'm correct. So you've got two notions, okay? And we'll see that these two notions are actually linked to integrable systems. So so we had to put some numbers on the faces on these quads, whether understanding them as ratios of diagonals or cross ratios. Okay, so how do you get that from in the real world? So one way is when you have, as I said, an embedding of your graph in the complex plane. Okay, but sometimes you don't have an embedding of your graph in the complex plane. Let's say you have a surface in 3 dimensions. In computer graphics, they like these kind of things. How do you understand that as being a discrete conformal structure? Well, you have to locally identify the local tangent plane with the complex plane C. Whenever you know how to do that for one way or another, then you can put on each quad, you can put these ratios, whether of diagonal or cross ratio of the 4 points. So for example, if you begin with a triangulation in 3 dimensions, a triangle has a well-defined center, okay? The circumcircle center, okay? Whenever you take 2 adjacent triangles, you can put them in the plane with the 2 triangles and the 2 adjacent, circumcircle centers, and then you can compute. That is to say, you can locally identify these 2 triangles with the complex plane C and compute these ratios of diagonals or cross ratios. Another way, which happens in computer graphics as well, is when you have little cubes, a surface which is given by little cubes. This is actually the data that you get from a 3D scanner. A 3D scanner, you've got an object, and a 3D scanner which is scanning it like this. And whenever it hits the object, it reflects in some direction. So the data that you've got is that there is a little cube here with such a normal vector to your object. And when you've got that, then you can project your little cube to the local tangent plane. And what you've got is some sort of parallelogram. And out of that, you can get as well these ratios of diagonals or cross ratios. Okay, so and these numbers, I call them a discrete conformal structure. Okay, whenever you put some numbers on each face, like Nyashpovsky, was saying last week, he had some capital F in each face. Well, I call these data a discrete conformal structure. And actually, where it came from, as far as I am concerned, is from statistical mechanics. So in my thesis, I was investigating the Ising model, and so the Ising model takes place on a graph, and on each edge you've got some interaction constants, and Baxter told us that this interaction constant actually has a geometrical meaning, and when you understand this interaction constant in this geometrical meaning, then you're equipped with this discrete conformal structure. I'll come back to the Ising model very in a moment. So actually, these discrete Riemann surfaces are used in computer graphics. So why is it so good? Well, there are several teams which work with that. So, for example, at Caltech or in Berlin and the Technion, or Gu and Yao. That's the Yao. Or in France, in RIA, are working with such a conformal parametrization. Why is it so good? Well, but if you have a surface in 3D and you want to map a texture to it, then if you do it linearly, if you don't do it in the right way, you have some shear that you interpret like a tilt. Okay, and it's going to give a wrong information of tilt. Okay, so that they much prefer conformal parametrizations, and anyway, conformal parametrizations seem to be very well adapted to natural pictures and things. Okay, so I said that my interest in the discrete Riemann surfaces came from statistical mechanics. So in the Ising model, it was already known, as I said, that Baxter that there was a special place which I called Z invariance Ising model, and what I did was to understand this criticality. So there is a phenomenon in the Ising model which is called criticality, and I understood this criticality as a compatibility with discrete holomorphicity that I just talked about. That is to say, at criticality, something very special happens, that there is an observable, which is called the disorder, the fermion, a disorder and a spin. And this special observable turns out to be discrete holomorphic when the Ising model is critical. And this is one way to write it. And that's right. So sigma is at x and mu is at y, a nearby face. Thank you. So there is an off criticality renormalized version of it, and leading to massive spinor, an elliptic deformation of this Dirac spinor. So Bajanov told you about that, I think, and there is work on these spinors by Rechetikin, Simanozoni, and Smirnov and Shelkak, who proved the conformal invariance of the Ising model using this trick, and also Pincal and Bohle in Berlin. Cardy generalized that to parafermions. So he proved that at criticality, the parafermions are discrete holomorphic in that sense, in the sense that I talked about. Okay, so I told you that whenever there is a similitude on each quad graph, on each quad face, you could say that this is a discrete holomorphic linear function. So how does it show? I mean, can you interpret that in terms of local similitude? Well, yes, you can. So first of all, you've got to picture your two dual graphs at the same place. Okay, so that's one way to do it. You have, let's say, you have vertices and the dual vertices which are in the middle of the faces. But this is a bit crumbled. Okay, you don't have space. Well, just deflate each of your faces and each of your dual faces by half to make some room, so that you can picture both dual graphs at the same time at the same place. Okay, so for example, this is the triangle lattice together with the hexagonal lattice, but they are drawn at the same time. So well, that's just one way to picture your two dual graphs at the same time, okay? So you map them by a certain function to another position in the complex plane. Well, if you can do it in such a way that each of your face is sent to a similar face, okay, that is to say here you see we still have regular hexagons and regular and equilateral triangles which fit together nicely, and they just kiss by one of the corner, then you say that here you have a discrete holomorphic linear function, okay? So that you can see geometrically that you have a discrete linear holomorphic function. Actually, the quadratic version can be plotted as well and has a geometrical interpretation as well in terms of circle patterns. So circle patterns are a particular case of cross-ratio preserving maps. So it was first a work by Thurston. So he was talking about circle packings, okay, when they are tangent. But here it's a slight generalization of it when you have patterns, okay, so they can intersect. So you have a pattern of circles, and you send them to a circle of patterns with the same combinatorics. You say that this couple is a discrete holomorphic map if each circle is sent to one circle and two neighboring circles intersect with the same angle. Okay, you have two neighboring circles and some intersection angles. Well, it happens that the cross ratio of the center of the circles and intersection points, the cross ratio of these 4 points is given by the intersection angle. It doesn't work in the linear case. So, I mean, so cross ratio preserving maps, a special case of them are circle patterns. And here you can see this notion of local similitude. Okay, so each circle is locally sent to a smaller or a bigger circle. So both of these versions of discrete analytic functions can be brought into the same form as Morera equation. That is to say, a function is holomorphic whenever its integral, the integral of f of z dz around any closed loop is null. Okay, that's the Morera equation. Well, actually, you can work out that the equation I gave on each quadrilateral lead you to the fact that these one forms are going to be closed. Okay, so here I've got a function sitting on the vertices of your graph. Okay, here I've got a one form sitting on the edges of the quad graph. How do you couple them? How do you couple a function on the vertices and the one form on the edges in order to have a new one form on the edges? Well, you just take the average of the values at the vertices. Well, there are two types of averages, whether you take the geometric mean or the diagonal, arithmetic mean of these values. If you take the geometric mean, it will lead you to the cross-ratio preserving maps. And if you take the arithmetic mean, it will lead you to the linear version. Okay? So, well, I'm not going to go into the details of that fact, but it simply relies on some simple change of variables leading you to a Hirota system. So that, and as you know, that the linearization of the geometric mean is the arithmetic mean. And so the version of this linear, the linearized version of this quadratic equation leads you to the linear version of discrete holomorphicity. That is to say, if here you see the manifold of all the cross-ratio preserving maps, its tangent space at each point is the space of discrete linear holomorphic function. Okay, so some notations. So now I'm going to go into the details on how close this theory of discrete linear holomorphic functions is to the usual complex analysis, and it's very close. Okay, so I'm going to go into the details of the notations to adopt some notations which are related to the usual notation in complex analysis, and show you which of the usual theorems of complex analysis you can generalize to this linear setting. Okay, so first you've got the chain complexes. Okay, so you all know these things. The chain complexes, linear combination of vertices, of edges, and of faces. You've got a boundary operator on that, which goes down, and it's null on vertices. The closed chains are in the kernel of this boundary operator, and the image of this boundary operator are the exact chains. So now you dualize that, and you look at the homomorphism from chains to the complex number, and you denote the evaluation between a zero form and a zero chain by function notation, integral notations, and surface integrals notation. Okay? So the dual of the boundary is called the co-boundary, and that goes up the co-chains, and it's defined by the Stokes formula. That is to say, df is simply the difference. So f is a function, df is one form, is simply the difference of values of the function. Alpha is a one form, d alpha is a two form. That is to say, it takes values on the face, and it's simply defined as the circulation of the one form around the face. Okay, this is very standard notations. And what's good about that is that you can define a wedge product between K and L forms to K plus L forms. I'm not going to go into the details of the definition of it. What I have to say is simply that this the discrete the differentiation is the co-boundary operator is a derivation for this product. That's what you need. That is to say, d of fg is fdg plus gdf. And all these Leibniz rule. There is one more important ingredient in that theory, is the Hodge operator. So more or less, the Hodge operator encodes the duality. Okay, but in two dimensions, the duality is connected to turning by 90 degrees. Okay, if I have one edge separating two dual faces, then this dual face is somehow orthogonal to it. Okay, so that's what it says. Okay, the value of the Hodge star of a one form on an edge is simply the value of the one form on the dual edge, okay, and multiplied by this discrete conformal structure. Okay, and this verifies that star square is -1. Okay, that is to say, it's really what I call discrete conformal structure. It really gives you some sort of conformal structure. So you can rewrite that f is locally a similitude by the fact that its Hodge star is itself multiplied by -i. The Hodge star of df is -idf. Out of that, you can define the discrete Laplacian by the same formula as in the continuous, and you end up with the Laplacian of a function at the vertex x is simply the weighted average, the weighted differences of all the all around a vertex x. And this is a very well-known formula. It's been defined for the first time in the 19th century. So it's a very long. It's been known for a very long time. Here I was talking about the case where this discrete conformal structure is actually coming from real, from orthogonal dual edges. We'll see in a moment how these generalize to more complicated situations. So you can define, and this works well with this Hodge star works well with the wedge product to define a scalar product, which is simply the usual L2 weighted product. So now I'm going to go into what changes when rho is a complex number. So we just saw that the Hodge star is simply the more or less the duality, okay, multiplied by this local discrete conformal structure. But actually, when rho, when locally these two dual edges are not orthogonal, you see it's a little bit more complicated. Okay, so when rho is not real, it's a little bit more complicated, but still, this it gives rise to a well-defined scalar product. And the L2 norm of df for a function gives you the Dirichlet energy, and this it's related to the Laplacian. You see that the gradient of that guy here is the Laplacian. So the minimums of the Dirichlet energy are given by the harmonic functions, the functions which are in the kernel of the Laplacian. You can set up as well a conformal energy, which is the L2 norm of df minus I star df. We saw that this thing is null on functions which are discrete holomorphic, and you can relate this conformal energy in the usual way to the Dirichlet energy. So this is simply to say that things are going mostly as in the continuous case. The Laplacian is a little bit more complicated when these rows are complex, but okay, anyway. So I said that when rho is real, this is the usual Laplacian known for 150 years, which is the weighted differences of values along the neighbors of a point. Okay, in the complex case, it involves the whole, not only the values on the graph itself, but on the dual as well. So this is a new Laplacian.
50 years ago, did they already include obviously modes?
Yes.
Why need to look at that?
Well,
Is there a motivation?
the motivations are physics. Like one way to look at these rows is to understand one graph as being a set of springs, and these rows are simply the stiffness of the spring, and this is nothing but the force which is pulling on x. Okay, it's the sum of all. So here you've got a point which is pulled by neighbor springs, and this is simply the sum of the force. Okay, and for it to be in equilibrium, then you need that the sum of the force should be 0. Okay, so that's one way to look at these rows as the rigidity of the springs, the stiffness of the springs. There is as well an electrical analogy of it. You look at it as being a network of conductors, and the conductance here, which is the inverse of the resistance, is telling you what is the flow of currents going out from a vertex. So here you would have the potential at each point, and this would be the intensity going through one edge, and you want at equilibrium that the sum of the intensity going from each vertex is null. Okay, see? But here for this term, when rho is complex, I guess there is as well an analogy by taking plates. Okay, not only rods but plates of elastic material or conducting material. I expect that, but I haven't proved it.
So they were not thinking, in other words, of discretization of the classical. This is this came up naturally.
Yes.
So
Yes. So there are some little problems. I mean, the fact that you have these to deal with twice as many graphs. Okay, the graph is dual, and to play with the graph, it's dual, and the diamond graph of quads. Okay, so now the relation with integrable systems. Well, it turns out that this system is integrable whenever you have whenever you can come up with these discrete conformal structure as coming from rhombi. Okay, that is to say, all these quads are now rhombi. Okay, so now there is behind that there is an integrable system, and it comes with equipped with a Darboux-Backlund transformation. So how is that? Well, let's say you have a solution. Okay, you have a discrete holomorphic function. Okay, sitting on your graph. Okay, and out of that you're going to build a family, or two complex parameter family deformation of this solution. Okay, this is called the Darboux-Backlund transformation. So how do you do that? So on your graph, sitting, let's say we're going to think of this graph as sitting horizontally. You're going to duplicate this graph on another layer, and between these layers you're going to put some extra conditions. So horizontally, you've got on each face, you've got an equation. Okay, let's say whether that the ratio of the diagonals is preserved, or for the quadratic version, that the cross ratio is preserved. Okay, we're going to put above each edge a vertical quad. Okay, and we're going to impose on these vertical quads the same equation as we had horizontally. So it's exactly the same as what Marchek was talking about last week. Okay, so please be careful that the ratio of diagonals here can be expressed by the sum here divided by the sum here. Okay, so here the ratio of the diagonal here and there is can be written. Okay, so here on this vertical faces, I'm going to ask that the value here on these quads verify that the ratio of the function here is given by this ratio, which is simply here I had some difference x minus y plus lambda, so I'm going to put a lambda vertically. Okay, on all the vertical above each vertex, I'm going to put an edge, a vertical edge, and I'm going to put some rapidity on this vertical edge, which I call lambda. Okay, and I'm going to impose that on these vertical faces, the ratio of the diagonals, or the ratio of the cross ratio. Okay, that's the same story for the cross ratio. Is the same as the one I put in by hand. Okay. So whenever I give a first solution here at that point, and I impose this equation, because I know I already have these green values are already given. Okay, I want to deform them. If I give you a value here, then the value there is determined. Okay, by rational fraction in terms of these values. So it's linearly determined in terms of these values in rational fractions in terms of these lambda. Okay, so you can do the same trick for this face, where you put another ratio of diagonals here, and you give then a value at that point. So you could have gone the other way around the face. Okay, but the fact is, whenever these discrete these x, y, x prime, y prime are making up rhombi, then it's the same thing. Whether you go along the blue or the red path, you end up with the same value. Okay, that's integrability as 3D consistency. So one way to look at it is to divide this cube into two hexagons that you split, whether this face here, okay, this half cube here, or this half cube there. So whenever you've got 6 values here, they are over-determined because any 3 of them determines the value there. And so you've got an algebraic constraint on these 6 numbers, and that's exactly the same as the constraint on these 6 numbers. Okay, that's one way to look at it, as more related to the Young-Baxter equation, which is more known from where I come from.
What was the rhombic constraint? Was that rows?
These rows come. Yes, these rows come from rhombi.
A direct geometric sense.
Yes,
of length.
that's right. Of the ratio of the length. Ratio of dual length.
Can you just express it also in the rows?
Yeah, you can capture that in the...
Rectangular lattice, probably just a straight on a row that you can see right down.
Yes, yes. So you can forget about the rhombi, and then you write everything in terms of rows. Yes, you can do that. Around each vertex, you'll have that the row satisfies some condition.
So for instance, for the cubic lattice.
Yeah, for Z2, it's the case. I mean,
Yeah.
squares
Would the rows just
are
be one
rhombi.
in that case?
Sorry?
For Z2, would the rows just be one?
Yes, all the rows are 1. That's right. Exactly right. All the rows are 1 for the Okay, so now I'm coming to the exponential. So you've got this quadratic Becklon transformation as well. Okay, so here once again you've got these cross ratio preserving maps, manifold, and you've got this Becklon transformation which acts on them and deform them. Okay, so there are 2 parameters for it, and if you take the 1 point, so you take one solution, you deform it to a certain other solution, and you can Becklon transform back that second solution. Okay, but it's actually not going the same way. Okay, so that is to say, these 2 things don't commute, but when you put the right things, you come back to the same point. Okay, so you can come up and come down. Okay, but actually at the linear version, if you differentiate that thing, you get a homomorphism of you get a linear map of the tangent space, and this linear map is actually not injective, and you can take its kernel, and this kernel defines for you some very special functions. That is to say, okay. Linear, discrete linear holomorphic functions, which are in the kernel of this composition, and this turns out to give you, when you take all the lambdas and you take different values for this lambda, it turns out to give you a basis of this space. Okay. It looks complicated, but actually it's not. So it goes back to Jacqueline Lyon-Ferrand. Oh yeah, I didn't mention that this theory in the linear case of Z2 was done. It was on the slide, but I didn't read it. It was first done by Jacqueline Lyon-Ferrand in the 40s, and then picked up by Duffin, who generalized it who showed that the rhombi case was very important. And so already in Jacqueline Lyon-Ferrand there were some expression for this exponential in the case of Z2. It appears as well in Neyhoff and Capelli in the 80s as what do you call them? Plane wave functions. And so you can write them like this, and it's you already know this very well-known formula for the exponential. It's the limit of 1 plus z on n to the n. Okay, this in capital O of z square on n. But there is actually a version which is a bit better. If you take 1 plus z on n on 2n divided by 1 minus z on 2n to the n, and this is this converges much faster to the exponential. And this is simply a generalization of that case when you don't go from O to Z directly in n steps of the same direction, but in n steps of the same length, but different directions. It actually doesn't depend on the path that you take, which is a bit surprising. Okay, so the path that you take on this rhombi graph. Okay, so that here, all these little edges are edges of rhombi. Okay, so as I said, it's already appeared in Neyhoff. So D'Oliva, Grinevich, Nishpovsky, and Santini actually generalized that plane wave solutions to spectral parameter here, lambda, which are not simply complex numbers, but on more generalized, more general spectral curve, the Riemann surface with some fixed points, by the finite gap Krishev construction. It's a very interesting thing. Okay, so now, as I said, these discrete exponentials, these planar waves, give you a basis of discrete holomorphic functions. And you can actually work out the linear combination of this exponential, which are which fulfill some conditions. For example, you look at the Graal of discrete harmonic theory, which is called the green function. The green function is the inverse of the Laplacian. Okay, and so it's a function which behaves like the logarithm. Okay, in the continuous case, the Laplacian hit on the logarithm is 0 everywhere and a delta distribution at the origin. So it's just exactly the same thing here, and it actually, so it's a discrete version of the logarithm. So I said that we've got the notion of logarithm, and we can actually compute it. It behaves like the logarithm. It's a real function on black vertices or on green vertices, and a pure imaginary function on the red vertices. So on the green vertices, it's the real part of the log, and on the red vertices, it's going to give you a non-well-defined, a multiply defined argument.
Lambda is still this Beckman parameter. You're still thinking of this kernel.
Yes, that's exactly right. Yes, here. But as I said, they are not very complicated. Okay. No. I presented them in a more general way here. Okay. So in a more general way, you can define these things at other points than simply rhombi. That's what I was saying. Okay. But it's really when you have rhombi that they are really interesting. That you can, but there should be deformations of these formulae at other points than rhombi, and for other spectral curves than just the complex plane.
What is the contour?
Sorry?
There's another thing that I the contour. See?
The contour, yeah, it's very important. The contour here is, so as I said, these Beckman transformation, they involve some rational fractions in terms of the slopes of your rhombi. Okay, so these things are rational fractions. They have poles, and so this curve turns around all the poles of these rational fractions in a quite special way. Okay, related to x. So you take a half line. Okay, not going into the details, but you're right. It's absolutely crucial. Okay, so when you differentiate this exponential with respect to the spectral parameter, you end up with a notion of discrete polynomials, and you can see that they have a nice, you can picture things, okay? But as I said previously, I don't know exactly what to do with what happens right at the middle, at the origin. I don't know what it means to have a higher degree 0, okay? For that matter, a higher degree pole. I don't know what that means. But you can when you are in this rhombi case, you can integrate and differentiate. So you have some differential equations. So these polynomials and exponentials behave just as you in the continuous case. That is to say, the derivative of the exponential is lambda exponential lambda z. Okay, so there are some connections with soliton theory. If you take the continuous limit of this Q1 delta equals 0 equation, you stumble upon some equations which are related to solitons. And you can as well have all this machinery of integrable systems applied to this theory. So you have as I said, the value at one point can be defined from the value at the three other points in terms of some rational fractions, and you can put that into a zero curvature representation. So here I'm Z2. Okay, I'm in Z2. That's actually Z to the D, but it doesn't matter much. Let's think about Z2, and so you can encapsulate one function little f as a moving frame in terms of polynomials, matrix valued polynomials moving frame, which give you some function satisfying some recurrent relations. Everything here are rational fractions in terms of lambda, and when you ask that this matrix valued function here is meromorphic in lambda with poles whose positions and order do not depend on the place where you are, you call that isomodromic solutions. And it happens that this green function I was talking about is an isomodromic solution. Okay, so I'm just going to hint at ways to look into the direction of Riemann-Roch, discrete Riemann-Roch theorem. So we said that a function is holomorphic whenever its df is so its associated one form is eigenvector of the Hodge star, and when of course it's closed, okay, because it's exact. So you say that the one form is conformal when it's closed and it's an eigenvector of the Hodge star. That is to say, its value on one edge is related to its value on the dual edge. You can factorize the Laplacian into two. What did I write here? Yeah, into you have. Okay, let's forget about that. So I just summarize here things that you can prove in this discrete case. So you have the adjoint of the coboundary. You have the Hodge decomposition of forms into exact, co-exact, and harmonic ones, and the harmonic are whether holomorphic or anti-holomorphic. You have a Weil-lemma, some green identity that we as well saw in the Mieszkowski talk. Okay, so and now for this discrete Riemann-Roch theorem. So you can say that in order to have a pole somewhere, a pole of order 1, just say that the one form of type 1,0 has a pole somewhere if this somewhere, well, if it's locally non-closed. Okay, if it's non-closed at some point, well, you're going to say that here it has a pole. Okay, and the defect of closeness, you're going to call that the residue. Okay, that's very simple for order 1 pole. And then, if it's not, if you just free this condition somewhere, you're going to say that there it has a pole of higher order, but I have no idea how to define this order. Okay, so that leads you to a crippled version of discrete Riemann-Roch theorem, existence of forms with prescribed Poisson holonomies. So with these simple versions of poles of order 1 and zeros of order 1s, you can have a discrete Riemann-Roch theorem. So you can define the period matrices. You have you can define an Abel map. You have some Riemann bilinear relations. You can actually prove a continuous limit theorem whenever the thing is critical, when it comes from rhombi. And you have, as I said, the Dirac spinor. So I'm going to stop there. Thank you.
Any questions?
Can you say how the approach that you've presented here, how that compares with Novikov's approach?
Well, I don't know exactly. I'm not that keen on triangles, that's all I can say. I prefer quadrilaterals, but I don't know. I mean, I don't know exactly how to compare them.
I mean, does your approach have any advantages over the Novikov approach? Does it have any disadvantages?
Well, they're different and somehow a bit related, but I don't know exactly. I mean, they're siblings. I don't see that one is better than the other. I don't know.
Novikov's approach is not yet that without unidirectional Riemann surface.
Yes. And it's a bit, our approach is much more flexible in terms of combinatorics. You can have, I mean, for example, a Penrose tiling, you can define what is a discrete holomorphic function on that thing, for example. So it's quite flexible. But, okay, in the background, there is actually things which are important are only in Z2, okay? And out of that, you can compute a holomorphic function on Z to the D, with D being the number of slopes you've got in your graph, and that's all what matters. So Z to the D to the 2 is really what matters. So I guess with the equilateral triangles, you can as well capture more complicated combinatorics somehow.
I was thinking about these discrete equations from a kind of a PDE point of view. If I think about these lattice equations, for example, on the ABS list, as a function of two independent variables, those two independent variables are the discrete variables that live on the lattice. If I understand you correctly, the complex analytic theory you have here is for functions of the dependent variables in those equations. That is, x as a function of n and m, or k and l. K and L remain discrete variables. We're not talking about analytic functions of k and L, but of x, which is a function of k and L, in some sense. Am I right?
Well, yes, N and M give you vertices in my...
Right.
Yes.
So you're not developing a complex analysis in N and M or K and L. You're developing complex analytic theory for the nodes, the functions of those variables.
Yes, the functions on
Right.
N and M,
Right.
the functions of N and M. Yeah, that's right.
Because that's that's a kind of a dual point of view to what happens in differential equations theory, where if we're trying to solve for functions of the independent variables, we're thinking about those functions' analytic properties of the independent variables. So when we expand the solutions, for example, in a Taylor series, we're expanding in the independent variable, whereas here you're expanding in the dependent variable, if I understand things correctly.
Yes, I think you understand it correctly. Especially, I cannot compose maps.
Yes.
That's related to what you're saying. I cannot compose map. I don't know if I have a holomorphic function, discrete holomorphic one, and another one.
Yes.
I don't know how to compose them. Thank you. Actually, not only composing, so the holomorphic functions have two multiplications, whether composition, which I don't know how to deal with, and pointwise multiplication, which as well I don't know how to deal with, unless cheating and defining the product as coming from the basis given by exponential, for example, and imposing that exponential lambda z multiplied by exponential mu z is equal to exponential lambda plus mu z, for example. But this is cheating. Okay? It's not pointwise multiplication. So maybe there could be some composition which would be related to some kind of cheating this way. But yeah, you're right. It's a very interesting point.
Constructional theory of associated theta functions associated with the discrete liberal surfaces.
So you can define a basis of holomorphic forms on a compact surface. So it has the right dimension, provided that you divide by 2, because there are these two dual graphs. So you can define the Abel's map, the Jacobian, and the map from your graph to C to the G, quotiented out by the lattice of monodromies of these one forms. But apart from that, I don't know how to define this theta function. I mean, so you've got period matrices. So you can define theta functions associated with these period matrices, but I don't know how they're related to my theory of discrete Riemann surfaces. Yeah. One point is that I don't know how to quotient things. And out of theta functions, you need to multiply them together and to divide. And I don't know what. I don't have theta functions. I don't have tau functions, but you have a tau function, discrete tau function. So maybe go in that direction.
Can you also ultra-discretize this theory of discrete Riemann surface?
Sorry?
Ultra-discretize?
I don't know. Actually, I haven't looked into the matter.
On one of your last slides, you dropped the term rapidities for the lattice variables alpha j. Could you elaborate on this link with vertex models and lattice approximations to relativistic quantum field theories that obviously is suggested by rapidities and continuum easing and all that?
Yes.
I mean, you have been talking about the mathematical aspects, but what about these applications of this in this class of models? Apparently there is, for these alphas, a notion that they are the rapidities of one of these models I'm alluding to. Could you elaborate on that?
So the wide dream of my PhD advisor, Daniel Benquin, was to understand statistical mechanics, integrable statistical mechanics models in the finite setup as discrete conformal field theory. Okay, that is to say, to try and find the traces of conformal blocks, of discrete conformal blocks in the finite setting, and to try and write observables and decompose them as Belyavin, Polyakov, Samologikov have been doing in the continuous conformal field theory, as sums of holomorphic times anti-holomorphic functions on the moduli space of the underlying Riemann surface. So here in the Ising model, we're almost there, because we showed that this observable, the fermion, was discrete holomorphic when the model was critical. And this criticality, which was understood geometrically by Baxter with these Z invariant models. So you look into Baxter, and it's already there. So you have some rapidities on edges. So you have a lattice where the interaction constant on each quad are given by some ratios of rapidities. The rapidities sitting on edges. And so there is a simple relation between these rapidities thought about as interaction constant in the Ising model and the angles of rhombi in this geometry.
So how about the generalization to vertex models? Like the sixth vertex is the critical limit of the eighth vertex, and it should also fit this picture then.
So so one part of the story of finding a discrete conformal field theory is about understanding the operator vertex algebra, and how when you take some fields and then you multiply them, they decompose into primary fields. And so in in Australia with Paul Pierce, I've been looking into the matter because in the Ising model it's a bit too simple. There are not that many things, so that you cannot see this algebra that much. A bit, but not that much. So in these more complicated integrable models, like the ADE models or Andrew Baxter Forrester models, you have more elaborate algebras. And with Paul Pierce, we've been identifying what would play the role of these discrete vertex operator algebra elements, and finding how they behave. So we actually put them along seams. So your statistical mechanics model is taking place on the surface. You take a loop and you insert along that loop some conformal boundary conditions, and you see when you put several of them how they decompose into one. So we showed that there was a discrete counterpart to conformal field theory vertex operator algebra, but we didn't succeed in going the way to analytic theory. I mean, into discrete complex analysis, and understand them as we did for the Ising model, as I did for the Ising model. So I'm not answering the question. I understand, but so no. Short answer.
Idea of where it goes.
Sorry.
It does give some idea of where it goes in applying
Yes.
to these other class of discrete integrable systems that is not so much represented in this meeting.
Actually, it's been used in percolation theory. And so Smirnov, Stanislav Smirnov has proven the conformal invariance of percolation using the theory of discrete holomorphic functions. A bit slanted, and actually Novikov would be pleased because it was on triangle. The same thing is looked into for other kind of statistical mechanics models. Dimer models, for example, which are related to the Ising model as well.
So let's thank our speaker.